A tiny knot of space is blasting impossible energy at us. It doesn't fit any physics we use to explain stars. Night at the observatory felt like standing under a dark ocean. The anomaly is a bright, localized source unlike a normal star. This matters because our energy budgets and emission models suddenly fail. Detectors recorded steady radiation across radio and X-ray bands. The signal pulsed for hours, then faded, then flared again. Flux measured about 10 to the power of -12 watts per square meter, so the immediate point is a real, multi-wavelength anomaly we must investigate. The dish rotated slowly, its metal face catching faint starlight. The anomaly first appeared in that exact sweep of sky. In plain words, it is a compact source with strange radiation. This matters because spectra tell us temperature, density, and motion. Detectors showed a spectral shape that did not match thermal emission. Usually, hot plasma produces thermal spectra, and shocks create broader lines. Here, photons peak at higher energies, with odd narrow spikes. For example, one flare showed millisecond spikes inside hour-long emission. So the core observation is a recurring, multi-wavelength burst from one tight spot. The anomaly spectrum refuses to fit any familiar emission model. In simple words, the light does not come from hot gas alone. This matters because spectra reveal temperatures, particle energies, and magnetic fields. Measurements show missing emission lines where they should have appeared. Photon energies extend farther into hard X-rays than expected. Timing shows millisecond spikes nested within hour-long flares. For instance, detectors recorded spikes every few milliseconds during a flare. So the anchor here is spectral shape combined with timing that defy models. Teams ripped open raw data and hunted for any bit errors. They reprocessed timestamps, checked clocks, and tested cabling integrity. This matters because instrument faults mimic exotic signals all too easily. Independent observatories then pointed different arrays at the same coordinates. Each array, using different receivers, recorded matching timestamped spikes. For example, 3 separate arrays reported coincident spikes within microsecond windows. So crosschecks strongly suggest the signal is genuinely astronomical and not an artifact. Our usual suspects include magnetars, microquasars, and pulsar wind nebulae. In plain words, these are extreme objects powered by gravity or magnetism. This matters because they explain many strange flashes we observe. But models for those sources predict thermal tails or predictable decay laws. For instance, magnetar bursts typically peak differently and cool predictably afterward. Numbers help. Magnetars release around 10 to the power of 39 joules in big flares. So standard astrophysical sources struggle to reproduce both the spectrum and timing together. One bold idea is a microscopic black hole evaporating nearby. In plain words, it would emit Hawking radiation as it shrinks. This matters because confirming it would prove quantum gravity effects directly. As it evaporates, particle emission ramps up, producing a hard spectrum. Models show burst durations and energies depend strongly on the black hole mass. For example, a black hole of about 10 to the power of 11 kilograms would emit intense radiation. So tiny black hole evaporation could match several observed features. Another idea points to unknown particle interactions in dense plasma. Simply put, new particles could convert mass into light unusually efficiently. This matters because it would extend particle physics beyond the standard model. Mechanically, particles could couple and then decay rapidly into photons. Laboratory experiments cannot yet recreate the required extreme densities. A testable signature would be identical energy peaks across repeated flares. So finding repeatable energy peaks would strongly support particle-driven emission. Observers launched coordinated campaigns across wavelengths and detectors. They will timestamp photons to microsecond precision and correlate events. This matters because precise timing separates exotic physics from ordinary sources. Teams will also search for neutrinos coincident with bright flares. A neutrino detection would favor hadronic processes, not new particles. Polarization measurements provide another strong discriminant among models. So coordinated, precise observations can rapidly narrow viable explanations. If proven exotic, textbooks would need revision and theories would expand. In plain terms, fundamental laws might gain new terms or extensions. This matters because nature dictates what physics must describe accurately. Impact could range from refined quantum gravity to unforeseen technologies decades later. A more immediate result would be improved detectors and analytic tools. For example, new instrumentation could detect even fainter anomalies routinely. So confirming an unexplainable anomaly would open entirely new physics directions. That knot of space still emits impossible energy, and those measurements remain robust. If you want calm updates, subscribe and check the public data releases for future observations.